So the one that we skipped in the video was y equals ln x. Y equals ln x. This is just another way of saying y equals log base e of x. Y equals log base e of x. And the e is the same thing that we studied last week, which is Euler's number. Euler's number, which is 2.718. So log graphs are the inverse of exponential graphs. So since exponential graphs have a horizontal asymptote, log graphs have a vertical asymptote. Exponential graphs get their asymptote from the number on the end. Vertical asymptotes are going to come from the number inside the parentheses, and that might be familiar if you guys remember the rational unit that had both. It had the vertical asymptote and the horizontal asymptote. We always got the vertical asymptote from the inside of the function, and the horizontal asymptote we always got from the end of the function. It works the same here. So exponential graphs, which we already studied, we got the horizontal asymptote from the end. The vertical asymptote you get from the parentheses. So vertical asymptote is going to be x equals 0. Now, with the exponential graphs, we had the important points were 0, 1, and then 1 and the base. And so with this, if we are going to say that the inverse of exponential graphs are logarithmic graphs, instead of having the point 0, 1, you're going to have the point 1, 0. And instead of having the point 1 comma the base, you're going to have the point the base comma 1. But in this case, for the ln graph, the base is always going to be e. So for ln, the base is e, which is actually 2.718. Now, ln is called the natural logarithm. And I think the reason that it's ln and not nl, I'm guessing, is that ln comes from like Latin of some sort, and it's probably like log natural, something, blah, blah, blah. But it's called the natural log. And it's actually a button on your calculator. It's right down here, right next to the 4. It's the ln button. And so the reason why the e to the x button is the second function of the ln button is because they're inverses of each other. They're related. Okay, so second ln was the e, and so the ln button is related to that. Okay, now another thing that is important for us that we did not do did not learn in the notes, but is going to be good to know, is that y equals log x. So this is just the log button on your calculator. Y equals log x is the same as y equals log base 10 of x. The log button is right above the ln button. There's the log button right there, right above ln. And this is called the common logarithm. And this would be the inverse of 10 to the x. You can see it in blue. It's the inverse of 10 to the x. And I think that's the common logarithm just because of how place value works and how decimals work. So if you think about when you move a decimal over, you multiply that number or divide that number by a power of 10. So we would have like the 10th place, the 100th place, the 1,000th place. The 10,000th place, you would just be dividing by 10, dividing by powers of 10. Same thing with a one-digit number is 1, and then a two-digit number is 10th place, then the 100th place, then the 1,000th place. To get from each place to the next, you're multiplying by 10s. So powers of 10 are very common, so this is common log. For us, we don't typically go to the 10th power because that makes a very large graph, and we don't use large graphs, so we are going to use bases like 2 or 3 or whatever, but log base 10 is considered to be the common logarithm. Very few people write log base 10, they would just write log. They wouldn't put the 10 there. It's kind of like with the square root. When you put a square root, you don't put the subscript, the little 2 in the square root like you do with a cube root. You put the little 3 there. Square roots are so common, you don't put a square root with a 2. You just put the square root sign. Same thing with a log base 10. You wouldn't put the 10 there. You just write log. And it's just because it's common. Yeah. All right. You use it a lot, and then it just becomes second nature. Oh, so if you want to put a different base, so with the 10, you wouldn't need to put a base there, you just use the button. But if you want to use a different base, you would hit the math button and then go up, up, and then this is how you do a different base. So math, up, up. Hit the math button, go up twice. And then it allows you to put a different base. Yep. Okay? All right. So let's go ahead and graph this. We have a vertical asymptote at 0. And we have the point 1, 0. And then 2.718 and up 1. So approximately right there. Now, these graphs follow a vertical asymptote, and so there's a point on these graphs where they basically become vertical, and your graphing calculators have a really hard time graphing that. And so to your graphing calculator, it looks like these graphs stop, and the only way that you know that they don't is that you understand that they don't. If you were to just look at it on a calculator, you would think these are square root graphs. But you have to know, oh, it's a log graph. It keeps going forever. So you have to be the one who knows this should be an arrow, not a stopping point. Okay? Because if you look at them on the graph, they look like they end. So if I go in here and I type lnx and I just graph it, you can't see it very well because it's right up against the x-axis, but it looks like it stops. And if I put some transformations in here, like if I move this graph to the right and then move it up a little bit so you guys can see it. Oh. To the right 4. Let me move it up some more. Up 7, let's say. There we go. See how it looks like it stops? It doesn't stop. It's just my calculator having a hard time graphing a vertical line. And that's because vertical lines are not functions, and our calculator doesn't graph things that aren't functions. So our calculator is not graphing the part of this that is approaching the vertical asymptote. It just stops. As soon as it starts to approach that vertical asymptote, our calculator cannot graph it any longer, and so it just doesn't graph anything. Okay, so this is a TI-84 issue where it just can't graph it that accurately anymore, and so it just doesn't show anything. And we have to understand, oh, the graph is still there even though it looks like it doesn't have anything. So this graph looks like it has no x-intercept, but it does. This graph would cross the x-axis, okay? Even though a lot of students will look at that and go like, oh, there's no x-intercept, and they would be wrong, okay? Does that make sense? It's something you have to watch out for. Yes?
What do you do if you got to find the x-intercept?
So with this one, I would just do second trace, option number 2, look between 0 and 10, and my calculator would tell me the x-intercept is very close to 4. It's still there. The calculator just can't show it. The calculator's having a very hard time. And you can tell, actually, that the x-intercept is super, super close to 4. In fact, I wouldn't say the x-intercept is 4, even though my 3 decimal places are 0. I would say 4.00. I would have to go out there and I would make sure that it's not at 4, because based on my equation, my asymptote is at 4. So I would know the x-intercept couldn't be at 4. It could be very close, but not exactly. Yeah. Good question. Okay, let's go ahead and turn the page. So I think the one that I skipped here was example 4. So we're going to hop down to example 4. And we need to graph 2 times ln x plus 5 minus 6. So 2... What? So the exact value would be you having an ln in the answer, kind of like a square root. As soon as you get a decimal answer for something, it wouldn't be an exact value anymore. Same thing with ln's. As soon as you get a decimal, it's not exact anymore. So if we wanted an exact answer, and we'll learn about this because we're going to solve equations. As soon as you want an exact answer, you have to not plug it in the calculator, basically. Yeah, once we plug it in the calculator, we're going to be getting approximate answers. So 2 ln x plus 5 and then minus 6. And everybody's typing this in, right? We're all getting that typed in? Okay, and if I hit graph, so how do I find the y-intercept? We're going to do the y-intercept first because I can't see the x-intercept. Second trace, number 1, plug in 0. Okay, so there's the y-intercept. So second trace, number 1, plug in 0, and we get the point 0, negative 2.781. So the y-intercept was pretty simple on this one. And then with the way our TI-84 works is that you can get y values that aren't on the screen, but you cannot get x values that aren't on the screen. So since this graph does not cross the x-axis on the screen, we will not be able to find the x-intercept without changing the window. So you can see that the curve is getting close to the x-axis, but it has not crossed it yet. It's on the positive x values, so I'm going to hit the window button, and I need some more positive x values so that I have a big enough number to see where it crosses. So we can change the 10 to a 20. Okay, and you can see it just barely crosses. Did everyone see that? How it just barely went over? What's the what? The dotted line. This is the axis, and the reason it looks like it has dots is because where's the it doesn't graph them. It doesn't graph them on the calculator, but it's at -5, and so it's right here. Yeah. Okay, so if we want to find our x-intercept, what should we do? Second trace number 2. 0 to 20 would work great. Okay, perfect, yeah. So it's 15.086. And to find the x-intercept, we did second trace, number 2. Okay. Are we good?
See, it's easy, but like I don't know, just something about like having like ln and stuff in the equation.
It intimidates students because it looks weird and it's not. This is like the first time that we have come across a graph where you truly have never seen it before, right? Like the logs were a little weird, but ln we like have truly not seen that as an equation before, and that makes it feel uncomfortable. Yeah. So it's okay to feel uncomfortable with these graphs. Just remember, they are just the inverse of exponential graphs. So all that's happened is you take an exponential and you trade the x and y. So when people say, like, what's an ln graph or what's a log graph, you just say, oh, it's an exponential graph where you just traded all the x and y's. If we need to know how to understand a log graph, that's what it is. It's exponentials where all the x's and y's have been traded. That's how we understand it. So what's the purpose of log? It is so that we can undo exponential. That's what the purpose is. Okay. So let's go ahead and let's do example 5. So, and we're gonna do all the things on it. Now, when you guys get to your assignment, there's no question on the assignment that asks you to do every single thing. On the assignment, it will say like, just give me the transformations, or just give me the end behavior, or just give me the domain and range. But for this, I want to practice finding like every little thing to make sure we can do every little thing. Okay? So first, let's find the transformations. Okay, left 1, up 5. What else? Reflect over x. Okay. What's the vertical asymptote? -1. So it would have been 5 if we were doing exponential and we were looking at the horizontal asymptote. Okay. So we're using the point 1, 0, base 1. And we have to do the transformations to the points. 2 is the base. Okay. So how do we reflect over x? Take the y. It'd be 1, 0 for the first one, and what would it be for the second one? 2, -1. So we took the y coordinates and we multiplied them by -1 to reflect them over x. Okay? How do we go left 1? Take the x and -1. Okay. And how do we go up 5? Add 5 to the y. 5, 4. Okay. So put my dotted line. And we got 0, 5, and 1, 4. There's the graph.
How do we know if we're gonna do that
Or the other way? So you can always start from the point that's furthest away and then go to the next point and then just follow the asymptote.
What about down?
So if you were to draw this other part, you can tell that these ones just kind of go out. So the exponential either go up or they go down. And then the logarithmic either go out this way or they go out this way.
I got that point, but how do you make sure that this a curve is the correct curve?
So kind of what I was telling Josh is that if you are having a hard time connecting the dots, you can start with the dot that's furthest away. And then you just know you're going to draw to the next dot and then follow the asymptote. So you know at least that part of it. And then this part, you know that it kind of is going to have this shape where if it's an exponential, it's either going to be tall up, tall down, and then logarithmic, they just go out. So that's it's just keeping in mind that it's going to be one of those two things. Yeah.
How do you type it in the calculator? Because it won't let you put the base to.
Math up. Mm-hmm. Okay. All right, so we've got to find the domain and the range. So domain, we got to do left to right and down to up. So domain is left and right. How far left does the graph go?
-1.
-1. Does it touch -1? No. Okay, parenthesis. How far to the right does it go? Infinity. Okay. And then the range, we've got down and up. How far down does the graph go? -infinity. It goes forever. It just goes slowly. And then how far up does it go? Forever. Okay. Increasing and decreasing. Okay, so if we get a stick figure and we have them walking, it only decreases. So for increasing, I'm going to say none. And then what value does it start walking? Is it -infinity or -1? -1. It actually never gets to a -infinity because the asymptote is blocking it. So it can't go left forever because the asymptote won't let it. So it's going to start walking at -1 and finish at infinity. So -1 to infinity for the decreasing. All right, max min. None. Oops. Okay, we got the x and the y-intercept. We know the y-intercept already. What's that? 0, 5. That was one of our points. Okay. X-intercept. We got to type this now. So we have type the negative first, and then how do we type a log? Math. Up, up.
You can't hit log.
Math, up, up. We can't hit the log button because the log button is base 10. We want base 2. So you got to do math, up, up, log base 2 of x plus 1 plus 5. So my window was at 20. That's not quite far enough. 30. 30 doesn't seem to do it either. What should I try next? 50? 50?
I think you just need to put like 1 and like 8.
There we go. Okay. So 50 worked. So now how do I find the x-intercept?
Put x equals 0, y equals 50. Or x
Okay.
equals 50, whatever.
Okay, so my left bound I'm going to use 0. My right bound I'm going to use 50. 31. Okay. So domain, range, increase, decrease, max, min, x, y. Is the graph continuous? Yes. Okay, end behavior. Okay, now I've done this a few times. I looked this, I saw examples of this, and I saw that when people did the end behavior for this, they had different ways of doing it than me. So I always said just look to the left forever. There isn't a left forever, so it's undefined. But I've seen people do that differently, so I don't want to practice something just in case that is not the way it is commonly done. So we are only going to do the right side end behavior, and then when I eat lunch, I'm going to talk to Dr. James and see how he does it. Okay, because he's brilliant. All right, so we're gonna do end behavior, but we're only gonna do half of it. Okay, and then after lunch, I will tell you guys what Dr. James said. Okay, so we're gonna do this side. We're gonna do the right side. So we're gonna say as x goes to the right forever, and then what do we see about the arrow? Does it go up or down? It goes down. It just does it very, very slowly. Really slowly. All right. Next one. What are the transformations? You got vertical stretch 2, right 3, up faux. Yep. Okay. We're doing example 6. We have a vertical asymptote at x equals 3. We have the point 1, 0, and what's the other point? Nope. 4. 4, 1, because the base is 4. Okay. And then we're going to do our transformation for vertical stretch of 2. So what are the points now? Not 2, 0. Still 1, 0, because 0 times 2 is still 0. And then 4, 2. So we took the y coordinates and we multiplied them by 2. Okay? And then we're going to do the transformation right 3. 4 and 7. Okay? And then we have to do the transformation up 4. So 4 and 6. Okay? And now we are ready to graph. So here we've got 3. We've got 4, 4. We've got 7, 6. Okay, so there's our graph. Okay. Domain and range. Domain, how far left, how far right? 3 to infinity. Okay, the range, how far down, how far up? Negative infinity, infinity. Increasing, decreasing. So if your stick figure starts walking, there's no decrease, only increase. Okay, what value is this where the stick figure starts walking? 3. And stops walking over here at infinity, positive infinity. All right, max, min. Mountaintops, valleys. None.
Do you even have to? Yeah, you have to write.
If they ask you, yes. Because if they ask you and you leave it blank, it looks like you don't know. No, because they just don't ever have that look. Yeah, they don't go up and come back down. They just go up or just go down. Yeah. All right. X-intercept, Y-intercept. It doesn't have one of them. Which one does it not have? Does not have a Y-intercept. The asymptote is keeping it from having a Y-intercept. Okay, let's go ahead and type this in on the calculator. So I'm going to type the 2 first. How do I type the log? Math up, up. Log base 4. X minus 3 plus 4. I'm going to hit the window button, and I'm going to take this and put it back to 10. Get my window back to normal. Okay, now it looks like it doesn't cross the x-axis. Does that mean that it doesn't cross the x-axis? Nope, that's not what it means. It's just the calculator struggling. Okay, so I'm going to do second trace. Option number 2. And what should I use for my left bound and right bound? 0 to 10. 3.063. I was very surprised that you were able to do that over an asymptote. I learned that today, that was allowed. I always thought you couldn't hop over an asymptote like that for doing left bound and right bound. I thought you'd have to stop, but apparently you don't. I used to like if I knew the answer was on the right side of the asymptote, then I would do like 3 to 10. So I'd use the asymptote and do that. Yeah. All right. Is the graph continuous? Yes. Okay, and then end behavior. We're going to wait till I talk to Dr. James to do the left side, but if we do the right side, when we look at the right side, what do we see? Goes on forever, and it goes up or down? Up. Marvelous. All right, you guys. So when I talked to Dr. James, so we can go back to example 5. So he said he would have done the same thing that I talked about doing, which is still looking for the left arrow, still looking at the right arrow. So with this one, if you looked at the left arrow, it cannot go left forever because it's stopped by the asymptote. And so, nope, that's not the y value, though. That's the x value. So when we look and we see, does the left arrow go left forever? It doesn't. And so for the y value, we would say y is undefined, because the furthest left that the graph goes is -1. It does not go past -1. It stops at -1. So if we were to try to get to -infinity, we'd never get there. So the graph is undefined at -infinity. It does not go left forever. It stops at -1. So when I talked to Dr. James, he said he would have done it the same way. And then for this one, same thing. As you try to look at the left arrow, the graph does not go left forever. Your y value would be undefined. It would stop. Yeah.
I had Dr. James as a teacher, and I never found out what his PhD was in.
It's in physics. He was a physicist. So he was a physicist for 30 years and retired. So he like did physics for a job.
He used to like come over and talk to me about turf life.
Yeah, and he so right now he is also a professor, a physics professor at Wake Tech, I think. In the evenings. So he's new. No, he does it in person. I think it's on like Tuesdays or something. He does it during the week.
How do you go all the way to Wake County?
I mean, you just drive.
Making the big money.
No, you make less as a it's called an adjunct professor when you're not tenured, and they make less than high school teachers do. So it's something you just do it for. If you do that and you're not doing it full time, you just do it for fun. High school teachers, they want to teach a higher level. I've thought about that's something he and I have talked about. I've thought about going and teaching college like calculus for fun. Well, he doesn't need this.